Space is not the silent void we imagine. It crackles with mysterious whispers, faint radio murmurs carried on vast clouds of interstellar gas. These are unexplained signals, cosmic enigmas that have defied explanation for decades. Today, we are going on a journey through 25 of the most baffling signals ever detected, a voyage into the deepest mysteries of the cosmos. By the end, you will understand the cutting edge of a scientific quest that is redefining our place in the universe. We will confront a signal so powerful it was scribbled WOW on a printout, and explore bursts of energy that cross billions of light years only to vanish in a millisecond. What do you believe is waiting for us in the cosmic static? The story of our search for cosmic whispers truly began with a single, electrifying moment in 1977. At the Big Ear Radio Telescope in Ohio, astronomer Jerry Amon was reviewing a data printout when he saw a sequence of letters and numbers so extraordinary he circled it and wrote a single word in the margin, WOW. That signal, known forever as the WOW signal, remains one of the most compelling mysteries in astronomy. It was a powerful, narrowband radio burst precisely at the frequency hydrogen atoms emit in the quiet of space, a logical channel to listen for if you wanted to be heard. It lasted 72 seconds, the exact time it took for the Big Ear telescope to scan that point in the sky, and then it vanished, never to be heard again. For decades, the source was a total enigma. But recent investigations have pointed to a fascinating and unsettling possibility. The signal appears to have originated from a direction rich with something very specific, a dense region of interstellar hydrogen gas near the constellation Sagittarius. This is not just empty space, it is a cosmic cloud, a nebula nursery where stars are born. This potential link transforms the mystery. If the signal came from a natural process within that cloud, what violent or unknown event could produce such a sharp, intense, and brief burst of radio energy on that one special frequency? We have never seen anything like it from a gas cloud before, but the other possibility is even more profound. If the signal was artificial, then its origin point becomes deeply strategic. A civilization might use the dense hydrogen of a nebula as a shield, a power source, or even a natural amplifier for a deliberate beacon. The WOW signal was not just a blip, it was a perfect candidate for a cosmic hello. Its connection to a specific, complex environment like a gas cloud does not simplify the puzzle. It complicates it beautifully, forcing us to ask whether we heard a natural cataclysm or the first faint echo of another mind looking back at us from the stellar nursery. The WOW signal was a solitary shout, but the universe soon revealed it was capable of something far more common and violent. In 2007, a young astronomer named Duncan Lorimer was sifting through old data from the Parkes Radio Telescope in Australia, a treasure trove of cosmic noise recorded years earlier. Buried in observations from 2001, he found something that should not have been there. A single spike of radio energy so intense it overwhelmed the telescope's detectors, a burst of raw power that lasted just 5 milliseconds. This was the Lorimer burst, the first recognized member of an entirely new class of cosmic phenomena, the fast radio burst. To understand its power, picture all the energy our sun releases over an entire month, compressed into a flash shorter than the blink of an eye. That energy had traveled across the cosmos for billions of years, a message in a bottle from an epoch when Earth was still a lifeless rock. The greatest mystery was not its power but its origin. The signal was so brief and so isolated that for years astronomers could not say where in the sky it came from, let alone how far it had traveled. Was it a local glitch or a message from the edge of the universe? The answer lay in the signal's own fingerprint. As the burst raced through the sparse gas that fills the space between galaxies, its journey left a subtle mark. Different radio frequencies within the burst were slowed down by minuscule amounts by this interstellar and intergalactic plasma. By measuring this delay, called dispersion, astronomers could estimate the vast distance the signal had traveled. The Lorimer burst dispersion was enormous, pointing to a source far outside our own Milky Way in a distant galaxy. This transformed the mystery. What cataclysm in a distant galaxy could produce such a staggering, fleeting flash? The leading hypothesis points to the most extreme objects we know, neutron stars. Imagine the core of a giant star, more massive than our Sun, collapsing into a city-sized sphere of pure nuclear matter. A magnetar is a neutron star with a magnetic field so powerful it could erase your credit card from halfway across the solar system. A sudden starquake on such a monster's crust, or the catastrophic collision of two neutron stars, could unleash a titanic magnetic shockwave, ripping through space and energizing any gas clouds in its path. This is where the interstellar medium becomes part of the story. That immense burst of energy did not travel through a perfect vacuum. It plowed through the thin gas clouds lingering between stars and between galaxies. These clouds acted like a cosmic lens and a filter, stretching the signal and imprinting it with clues about the long, lonely roads it traveled. The Lorimer burst was not just an explosion, it was an echo. Its very structure carries the faint signature of every diffused cloud of hydrogen and helium it passed through on its billion-year journey to our telescopes. It taught us that the universe is not just filled with these mysterious flashes, but that each one is a forensic record, a story of epic destruction written in the subtle language of scattered radio waves and interstellar gas. The discovery of repeating bursts shattered another assumption. We thought these cosmic flashes were one-time cataclysms, but then we found one that kept talking back. FRB 180,916 is not just a repeater, it has a schedule. For approximately 4 days, it fires off bursts in erratic clusters. Then, for the next 12 days, it falls completely silent. This cycle repeats with clockwork precision every 16.35 days. Think about that. In a universe dominated by chaos and random violence, here is a signal with a rhythm you could literally set your calendar by. This periodicity is a colossal clue, and it points directly to the environment around the source. Astronomers traced FRB 180,916 to a surprising home, not a lonely, ancient galaxy, but a vibrant, star-forming region within a nearby spiral galaxy. This is a place of cosmic childbirth, filled with young, massive stars and the dense, chaotic clouds of gas and dust that forge them. The leading suspect for the source is a young magnetar, the highly magnetized corpse of one of those massive stars. But a simple magnetar outburst cannot explain the 16-day schedule. Something must be governing its bursts, turning them on and off like a cosmic lighthouse. This is where the surrounding interstellar medium becomes a key player. One compelling theory suggests the magnetar is in a binary orbit, circling another star or perhaps a disk of leftover material. As it moves through its orbit, it periodically plows through a thick wind of gas flowing from its companion. For those 4 days when the bursts are active, the magnetar is in a part of its orbit where this dense gas cloud is thin enough for its powerful radio shockwaves to escape and reach us. When it moves behind the thicker part of the wind, the radio signals are smothered, absorbed by that shroud of interstellar material, creating the 12 days of silence. It is a natural valve, opened and closed by the regular motion of the object through its own messy, gaseous environment. This means the signal we receive is not just the raw scream of the magnetar. It is that scream filtered, shaped, and timed by the very cloud it is trying to escape. The periodicity is not coming from the engine itself, but from the environment that cages it. This transforms a mysterious flash into a diagnostic tool, allowing us to map the invisible structure of gas and wind around one of the universe's most extreme objects. It suggests that to truly understand these signals, we must learn to read the shadows they cast upon the interstellar clouds that surround them. The clockwork rhythm of FRB 180,916 proved these signals could be persistent, but it was just a single voice in what we now know is a cosmic chorus. The true scale of the mystery was revealed by an unassuming array of metal mesh in the mountains of British Columbia. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, was not even built to hunt for fast radio bursts. Its primary mission was to map the largest structures in the universe by detecting radio waves from neutral hydrogen gas across cosmic time. But its design, a stationary corridor of antennas that scans the entire northern sky every day, made it the perfect net for catching fleeting cosmic flashes. When CHIME came online, it transformed the field overnight. Before CHIME, we had catalogued a handful of bursts. Within its first year of operation, CHIME discovered hundreds, including dozens of the crucial repeating kind. This was a revolution in statistics. Suddenly, fast radio bursts were not rare, exotic events. They were happening all the time, a constant background crackle of the universe. The repeaters CHIME found were particularly strange. They did not all behave like the tidy 16-day schedule of FRB 180,916. Some would erupt in a frantic storm of dozens of bursts in a single hour, then go quiet for months. Others would emit just a few faint whispers spaced years apart. This bizarre diversity told astronomers something profound. There is not one single type of engine powering these events. We are looking at a whole zoo of different sources, each with its own personality and behavior, and almost all of them share one common trait. Their signals bear the unmistakable fingerprint of having traveled through dense, complex material. When astronomers analyze the structure of the radio waves from these CHIME repeaters, they see clear evidence of what is called scattering. The sharp pulse of the original burst gets smeared out, its edges blurred as it passes through turbulent clouds of charged particles. This is the signature of a signal fighting its way out of a messy, energetic environment. The most likely nurseries for these events are the chaotic regions where stars are born and die, places flooded with intense radiation, powerful magnetic fields, and thick clouds of gas and dust. A magnetar born in the wreckage of a supernova, for instance, would be sitting in the middle of a vast, expanding shell of its own stellar remains, a perfect fog of material to scatter and shape its radio screams. CHIME Growing Catalog is not just a list of mysteries, it is a population study. By showing us that repeaters are common and that their signals are consistently sculpted by intervening material, it forces a major conclusion. These are not isolated explosions in empty space. They are phenomena deeply connected to and often shrouded by the interstellar medium. The source of the burst and the cloud that surrounds it are part of the same story. To decode the signal, we must first understand the fog it is trying to shine through. This turns every detected burst into a double puzzle, a message about a distant cataclysm, and a detailed map of the invisible cosmic weather it passed through on its way to us. Just when we thought we understood the neighborhood of these bursts, the universe handed us a paradox. In January of 2020, the CHIME telescope detected a fast radio burst with a designation that would become infamous, FRB 20,200,120e. Its location was the first shock. This was not a signal from a distant, star-forming galaxy billions of light-years away. This burst came from much closer to home, originating inside Messier 81, a beautiful spiral galaxy that is one of our nearest intergalactic neighbors. The distance was staggering, but in cosmic terms, it was practically in our backyard. Pinpointing its exact location within that galaxy delivered the second, far greater shock. FRB 20,200,120e was not in a vibrant nebula or a region of young, blue stars. It was coming from a globular cluster. Picture a dense, spherical swarm of hundreds of thousands of stars, all bound together by gravity, orbiting the outskirts of a galaxy like a distant, ancient satellite. Globular clusters are cosmic retirement homes. They contain some of the oldest stars in the universe, stars that formed over 10 billion years ago, long before our own sun was even a cloud of dust. There is no active star formation here, no dense gas clouds giving birth to new suns. This environment directly contradicts the leading theory that fast radio bursts come from young magnetars, the newborn corpses of massive stars. You simply do not get young, highly magnetized neutron stars in a place where star formation ceased eons ago. This single detection threw a wrench into the entire machinery of our understanding. It forced astronomers to think outside the box, to consider entirely new types of cosmic engines that could lurk in these ancient stellar cities. One compelling alternative is the highly magnetized white dwarf. A white dwarf is the Earth-sized, fading ember of a star like our Sun. Under certain rare conditions, perhaps in a tight binary system within the cluster, a white dwarf could become magnetized to an extreme degree, creating instabilities that unleash a powerful radio burst. Another, more dramatic possibility is a collision. The core of a globular cluster is an incredibly crowded place with stars passing perilously close to one another. Could a burst be caused by the catastrophic merger of two ultra-dense objects, like neutron stars or white dwarfs, that finally spiraled together after billions of years in a slow gravitational dance? The surrounding environment is key to this mystery. While the cluster itself is old, it is not empty. The spaces between those ancient stars are filled with a diffuse, ionized gas, the accumulated winds and remnants of stellar evolution over countless millennia. This intracluster medium could play a crucial role. A collision or an outburst from an exotic object would send a powerful shockwave ripping through this tenuous gas, energizing it and producing the brilliant radio flash we see. The signal from FRB 20,200,120e, therefore, carries the imprint of this ancient environment. Its properties are a direct message from the heart of a stellar relic, telling us that the universe has more than one way to create these brilliant, mysterious flashes. It proves that the story of fast radio bursts is not a simple one, but a tapestry woven from different cosmic threads, some from the vibrant nurseries of youth and others from the silent, dense gatherings of extreme age. The paradox of a fast radio burst from an ancient star cluster reminds us how often our cosmic expectations are shattered. But sometimes the most tantalizing signals come not from distant galaxies but from right next door. In 2020, the search for intelligent life delivered its own breathtaking puzzle. The Breakthrough Listen project, a monumental scientific effort to scan the sky for technosignatures, detected a strange, narrowband radio signal. Its name was BLC1, and its apparent origin was the most shocking part of all. It seemed to be coming from the direction of Proxima Centauri, the closest star to our own Sun, a mere 4.2 light-years away. This was not just any star. Proxima Centauri is known to host at least one rocky planet, Proxima b, orbiting within its habitable zone where temperatures could allow for liquid water. The signal itself was a compelling candidate. It was a pure, persistent tone at 982 MHz, a frequency notably clear of common human-made satellite transmissions. For a moment, it seemed to check every box for a potential artificial broadcast. The discovery sent a ripple of cautious excitement through the scientific community. Here was a signal that matched the profile of a deliberate transmission from our closest stellar neighbor. The team, however, was rigorously skeptical. They embarked on a forensic process of elimination, hunting for any possible explanation other than an extraterrestrial source. They analyzed the signal's properties, its drift rate as the Earth and the source moved relative to each other, and most importantly, they searched for any human technology that could have mimicked it. The conclusion, after months of painstaking work, was a letdown cloaked in valuable insight. BLC-1 was almost certainly human-made radio interference, likely from a piece of electronics on the surface of Earth. Its characteristics, while unusual, could be explained by a process of radio frequency interference that cleverly mimicked the expected signature of a distant transmitter. Yet the case of BLC-1 is far from a simple story of a false alarm. It is a profound cautionary tale for signal hunters. Why did this particular instance of interference so closely match our theoretical models of what an alien technosignature should look like? It forced astronomers to confront the uncomfortable reality that our own planet is now drowning in a sea of complex radio pollution, and our filters are not yet perfect. The signal's apparent origin near Proxima Centauri was a cruel coincidence of timing and geometry, a reminder that the universe is full of misleading alignments. This episode did not close the book on the search. It wrote a crucial new chapter on methodology. It proved that the greatest challenge in finding a real signal may not be sensitivity, but discrimination, sifting the faint, hopeful whisper of another civilization from the overwhelming roar of our own technological echo. The ghost of BLC-1 lingers, a phantom that teaches us to hope boldly, but to question even more rigorously. The search for a signal from our nearest star ended in terrestrial static, but the hunt only intensified elsewhere. In 2015, a different kind of candidate emerged from a much more distant point. The RATIAN 600 radio telescope, a giant ring of metal panels nestled in the Russian Caucasus Mountains, detected a powerful narrowband radio spike. Its source was a star designated HD 164595, a Sun-like star nearly 95 light-years away in the constellation Hercules. The signal was strong, and it appeared to originate from the star's precise location in the sky. For a brief, electrifying moment, it seemed like another potential breakthrough. The star itself added to the intrigue. HD 164595 is remarkably similar to our own Sun in size and temperature, and astronomers knew it hosted at least one Neptune-sized planet. A civilization around such a familiar star was a compelling thought. The signal's intensity, if it were truly an isotropic broadcast beamed in all directions, would require a power source far beyond anything humanity could muster. But if it were a narrow, directed transmission like a focused beacon or radar, it fell within a conceivable technological range. The excitement, however, was short-lived. The scientific community quickly mobilized to re-observe the star. Dozens of telescopes, including the formidable Allen Telescope Array dedicated to the search for extraterrestrial intelligence, pointed toward Hercules. They heard nothing but cosmic silence. The most likely explanation, after thorough analysis, pointed back to Earth. The signal's characteristics strongly suggested it was a fleeting burst of interference from a secretive military or surveillance satellite passing through the telescope's field of view. This was another sobering lesson in cosmic false alarms. Yet, the case of HD 164595 was far from a waste. It served as a critical fire drill for the global astronomical community. The rapid international response to analyze and debunk the signal demonstrated a refined, rigorous protocol in action. It proved that scientists now have a systematic playbook for vetting such discoveries, one that prioritizes immediate verification and open collaboration over sensational speculation. This event sharpened the tools and tempered the expectations for the entire field. It reinforced a vital principle: a single, unexplained signal is a curiosity, but a repeatable, verifiable one is a revolution. The silence that followed was not disappointment. It was the sound of the scientific process working, filtering out the noise of our own world, so we might one day be truly ready to hear the real message when it finally arrives. While the search for intelligent life grappled with earthly interference, another telescope was quietly collecting data that would rewrite the history of cosmic bursts. Decades before the term fast radio burst was even coined, an observatory in Australia was already capturing them. The Molonglo Observatory Synthesis Telescope, MOST, was a unique instrument, a vast array of metal pipes stretching over a kilometer, designed to map radio waves with exquisite precision. Throughout the 1990s, it recorded a handful of strange, brilliant events. They appeared as highly dispersed bursts, their signals smeared across time like a voice echoing down a long corridor. Astronomers at the time were baffled. The dispersion measure of these bursts was so enormous it defied logic. If the signal was coming from within our own galaxy, as all known pulsars did, the amount of interstellar gas needed to cause that much dispersion would have been impossibly dense, like trying to see through a brick wall. The alternative was even more radical, that the bursts were coming from far beyond the Milky Way. But in the 1990s, the idea of an extragalactic radio burst that bright was considered almost heretical, a theoretical fantasy. So the Molonglo mysteries were filed away, unexplained curiosities in an old data archive. The truth would not emerge until years later, when Duncan Lorimer's discovery of his famous burst created a new category of cosmic phenomenon. Suddenly, astronomers had a template. A team went back, sifting through the old Molonglo data with fresh eyes, applying the new understanding of dispersion measures. The match was perfect. Those mysterious 1990s bursts were not glitches or local anomalies. They were fast radio bursts detected and recorded a full decade before the scientific community had a name for them. This historical rediscovery was a profound lesson. It demonstrated that these events were not new. The universe had been sending them all along. We simply lacked the conceptual framework to recognize what we were seeing. The Molonglo data became a precious time capsule, proving that the burst rate seen by modern telescopes like CHIME was not a fluke, but a consistent feature of the cosmos. It also highlighted a crucial point about the interstellar and intergalactic medium, that ghostly fog of gas. The extreme dispersion that so confused early researchers was the very clue that pointed to the truth. Those bursts had traversed an almost unimaginable volume of space, their radio waves braiding through the diffuse plasma that floats between galaxies. The delay imprinted on the signal was a direct measure of the total amount of that invisible material it had passed through. The Molonglo mysteries, once filed away as errors, became foundational stones, confirming that the universe is alive with these brilliant, fleeting whispers, and that every one of them carries within it a hidden map of the vast, empty roads between the stars. These historical bursts were ghosts in the machine, waiting for a name. Our modern telescopes, however, are now catching them in a torrent, and one instrument in particular has become a master at the hunt. The Australian Square Kilometre Array Pathfinder, known as ASCAP, is a field of 36 identical dish antennas working in concert across the remote outback. Its true genius lies not just in detection but in precision. By comparing the minute difference in a signal's arrival time at each separate dish, ASCAP can triangulate the location of a fast radio burst with astonishing accuracy, pinpointing its home galaxy within a matter of days. This capability has revolutionized the field. While CHIME tells us a burst happened, ASCAP tells us exactly where it came from. The flood of data from ASCAP has painted a new and bewildering cosmic portrait. The telescope has localized a vast number of bursts, and the overwhelming majority are one-time events, solitary flashes that scream and are never heard from again. More startling is the sheer diversity of their homes. ASCAP has traced these single bursts to every imaginable type of galaxy, from massive, dusty spirals actively forming stars to quiet, aging ellipticals where star formation ceased eons ago, and even to small, irregular dwarf galaxies. This random distribution is a profound challenge. If all fast radio bursts came from a single type of event, like a magnetar flare, we would expect them to be clustered in specific environments where young, massive stars live and die, the stellar nurseries that create these magnetic monsters. But the ASCAP data shows no such preference. The bursts are cosmic nomads appearing in grand galactic cities and quiet cosmic villages with equal indifference. This points to an inescapable conclusion. There cannot be just one explanation. The universe is likely using multiple, entirely different physical engines to produce these brilliant flashes. A cataclysmic collision in an ancient elliptical galaxy, a magnetic eruption in a star-forming spiral, and perhaps even exotic processes in dwarf galaxies could all be capable of generating a fast radio burst under the right conditions. ASCAP wall of unidentified transients is not a failure of understanding. It is a map of our ignorance, revealing a cosmos far more creatively violent than we imagined. Each localized burst is a clue, forcing us to abandon the dream of a single, neat theory and accept a messier, more fascinating reality, where the interstellar medium is not just a backdrop, but an active participant in a multitude of different cosmic disasters. Deep in the chaotic heart of our own galaxy, another type of signal was waiting to be heard. Between 2002 and 2004, a radio telescope in New Mexico detected something utterly strange from the direction of the Milky Way's core. It was not a millisecond flash like a fast radio burst. This was something slower, brighter, and eerily predictable. Astronomers named it the Galactic Center Radio Transient, GCRT, and it behaved like nothing else we had ever seen. Roughly every 77 minutes, it would erupt into a brilliant radio flare for about 10 minutes, then fade back into the background noise. It repeated this cycle for weeks, then vanished for years, only to reappear again later with the same steady rhythm. This was a completely new class of object. Pulsars flash with metronomic precision, but they are milliseconds fast and incredibly consistent. Flare stars can have outbursts, but they are messy and chaotic, tied to magnetic storms on their surfaces. The GCRT was something in between, a slow, ponderous, luminous heartbeat emanating from the most crowded and extreme neighborhood in our galaxy. The source sits just a few hundred light-years from Sagittarius, a star, the supermassive black hole at the galactic center. This environment is a cosmic pressure cooker, flooded with intense radiation, powerful magnetic fields, and swarms of stars orbiting at fantastic speeds. Any object living there is subjected to unimaginable gravitational stresses. So what could produce such a slow, bright, repeating radio pulse? One compelling theory points to a highly magnetized neutron star, but with a twist. Imagine a neutron star that is not perfectly aligned. Like a wobbly top, it could be precessing, slowly wobbling as it spins. If its magnetic poles sweep through a dense cloud of gas floating in the interstellar medium near the galactic center, that interaction could trigger a periodic flash. Every time a pole points into the cloud, it would funnel material onto the star's surface or accelerate particles, creating a bright radio flare. The 77-minute cycle would then be the precession period, the time it takes for the wobble to complete one full cycle. Another, even more exotic idea involves the environment of the black hole itself. Could the signal be coming from a magnetar in a very long, elliptical orbit around Sagittarius, a star? As it swings through the dense disk of gas and dust swirling around the black hole on its multi-month orbit, it might periodically plunge through a particularly thick clump of material, lighting up each time it passes. The GCRT remains an enigma because its slow, bright nature defies the quick, violent models we use for other bursts. It suggests a more gradual, almost rhythmic release of energy, one deeply connected to the unique and turbulent interstellar medium of the galactic core. It is a reminder that the heart of our own galaxy is still a place of profound mystery, where unknown objects pulse with a slow, deliberate light, their signals shaped by the fierce winds and tides of a supermassive black hole's domain. The slow, rhythmic heartbeat from our galaxy's core is a reminder that cosmic signals often defy our neat categories. This brings us to a pair of phenomena that, for a time, created immense confusion, a harmonious duo of celestial red herrings and hidden giants. First, we have the Puritans. For years, telescopes around the world, particularly the Parkes Observatory in Australia, would occasionally detect strange, dispersed radio bursts that looked for all the world like they were coming from deep space. They had the hallmarks of fast radio bursts, a bright flash with a signature smearing effect from interstellar gas. But there was a bizarre clue. These signals were only ever seen during daytime hours at the observatory, and they seemed to come from all directions in the sky at once. That is not how celestial objects behave. The mystery was finally cracked not by an astronomer, but by an observatory staff member who noticed the pattern lined up perfectly with lunch breaks. The culprit was a microwave oven in the facility's kitchen. When someone opened the oven door before the timer finished, the device's magnetron emitted a brief burst of radio waves. That burst would reflect off the metal walls of the building and then off the surrounding hills, finally scattering into the telescope's dish from multiple angles, creating the illusion of a celestial signal arriving from everywhere. The Puritans were a masterclass in humility, teaching astronomers that the most insidious noise in their data could come not from the cosmos, but from a mundane appliance just down the hall. It forced the development of stricter filters and a deeper skepticism, a crucial shield against false hope. While Puritans were earthly ghosts, another signal was a true cosmic object hiding in plain sight, the rotating radio transient, or RRT. For decades, we knew of two main types of neutron star beacons, the steady, metronomic pulsars and the erratic, magnetically stormy magnetars. Then, in the early 2000s, surveys began picking up something new, single, incredibly bright radio pulses that would appear out of nowhere and then vanish, sometimes for hours or even days before another solitary pulse would erupt. They were not periodic like pulsars, nor were they the violent, multi-wavelength outbursts of magnetars. They were the cosmic equivalent of a shy giant clearing its throat once a day. These RRTs are, in fact, neutron stars, but they represent an extreme end of the pulsar family. Their radio beams are thought to be exceptionally narrow or unstable. Most of the time, that beam simply misses Earth as the star rotates, and we detect nothing. But occasionally, when the alignment is just right, a fleeting, powerful flash sweeps across our planet. Discovering them required new analysis techniques, sifting through mountains of radio data to find those singular, brilliant spikes that traditional pulsar searches would discard as noise. RRTs revealed an entire hidden population of neutron stars we never knew existed, objects that spend most of their lives in radio silence, only occasionally announcing their presence with a startling shout. They are a testament to the fact that the interstellar medium is not a passive screen, but an active sculptor. The gas and magnetic fields between us and these erratic pulsars can amplify or scatter those rare pulses, making them appear even more bizarre and fleeting. Together, the Puritans and RRTs form a perfect lesson. One shows us the critical importance of ruling out our own world before claiming a cosmic discovery, and the other shows us that even when we do, the universe still has entire classes of objects waiting to be found, blinking erratically in the vast dark. The hunt for cosmic whispers has always been shadowed by the ultimate question: could any of them be a message? Among the static and stellar explosions, a handful of signals have briefly flickered with that tantalizing possibility. The first of these technosignature candidates emerged from a sky survey in 1997, a project analyzing vast amounts of data from the SETI Institute's Project Phoenix. Within that digital haystack, researchers identified a signal designated SHB02+14A. It was a narrowband radio whisper centered on a frequency of about 1,420 MHz, a quiet region of the spectrum notable for being the emission line of neutral hydrogen, the most common element in the universe. The signal seemed to drift, changing frequency slightly over time in a way that could be explained by the Doppler shift caused by a planet orbiting its home star. For a moment, it seemed to check several theoretical boxes for an artificial beacon. Yet, the excitement was muted and short-lived. The signal was incredibly weak, and crucially, it was never detected again despite repeated, dedicated efforts to listen for it. Without that essential repeatability, the signal faded from serious scientific scrutiny, becoming a footnote, a ghost that demonstrated just how elusive and demanding the standards of proof truly are in this field. A few years later, a much bolder claim emerged, one that seemed to leap across the cosmic void. In 2003, a team analyzing data from the massive Arecibo radio telescope in Puerto Rico announced the detection of a powerful radio signal apparently originating from the direction of the Andromeda Galaxy, our nearest major galactic neighbor over 2 million light-years away. The implications were staggering. A signal that strong from another galaxy would imply a civilization capable of harnessing energy on an almost unimaginable scale, perhaps using their entire star as a power source for a deliberate galaxy-spanning beacon. The scientific community immediately mobilized to scrutinize the finding. The verdict, after intense statistical analysis, was a sobering one. The signal was deemed far more likely to be an unusual but natural statistical fluctuation, a rare peak in the ever-present radio noise of the universe that, by pure chance, aligned with Andromeda's position. It was a lesson in cosmic coincidence, a reminder that the universe can produce patterns that tease our pattern-seeking minds, even from the chaos of random noise. The desire to find a pattern, however, is the engine of the entire search. This drive was epitomized by a pioneering effort 3 decades earlier known as OSMA 2. In 1973, astronomers used the giant radio telescope at Green Bank, West Virginia, to conduct a follow-up to the very first modern SETI experiment, Project OSMA. This time, they meticulously observed over 600 nearby stars, scanning for any sign of narrowband radio signals. The project did not find a clear, unambiguous beacon, but it did detect something perplexing, a handful of intriguing, unexplained narrowband signals that appeared and then vanished. These signals were not publicized as potential alien messages because the researchers themselves could not rule out terrestrial interference or instrumental glitches with absolute certainty. Yet, their very presence in the data was significant. OSMA 2 illustrated the long, patient, and often frustrating nature of the search, a process built on sifting through countless false alarms and ambiguous blips in the hope that one day, one signal will refuse to be explained away. These 3 candidates from SETI 02 plus 14 are to the Arecibo anomaly, and the whispers of OSMA 2 form a crucial lineage in our quest. They are not failures but benchmarks. Each one forced the development of better technology, stricter protocols, and a more disciplined skepticism, honing the tools we use today to listen for a real hello in the cosmic static. The search for cosmic patterns has always been a race against time, hunting for signals that flicker in milliseconds or repeat every few days. But what if the universe operates on a much slower, more deliberate clock? The Low-Frequency Array, LOFAR, a sprawling network of radio antennas across Europe, recently uncovered a new class of mystery that forces us to ask exactly that. LOFAR listens to the sky at very low radio frequencies, a part of the spectrum that reveals a different, more patient universe. There, it has begun detecting objects astronomers are calling ultra-long-period radio transients. The name says it all. These are sources that erupt in brilliant radio waves, but their cycles are not measured in milliseconds or even minutes. They brighten and fade over astonishingly long periods, from many minutes up to several hours. This is a timescale we simply have no natural explanation for within our current models of stellar corpses. Imagine a lighthouse whose beam takes 3 hours to sweep past you instead of 3 seconds. What kind of cosmic engine could possibly have such a slow, majestic pulse? the leading theories point to objects we know, but in extreme and unfamiliar configurations. One candidate is the ultra-long period magnetar. We know magnetars as neutron stars with unimaginably strong magnetic fields that produce violent, rapid flares. But what if a magnetar could spin so incredibly slowly that its magnetic field takes hours to complete a single revolution? The physics to create such a slow spin is baffling, but if it exists, its radio beacon would sweep across space with this ponderous, hours-long rhythm. Another possibility is an entirely different beast, the white dwarf pulsar. A white dwarf is the Earth-sized remnant of a star like our Sun. While we have found a few white dwarfs that pulse in other wavelengths, a true radio pulsar version has never been confirmed. A highly magnetized white dwarf, spinning with a period of hours, could theoretically produce the kind of slow, bright radio flashes LOFAR is seeing. But here is where the interstellar environment becomes crucial. For either of these objects to produce a radio signal we can detect, they need to be interacting with something. A solitary, spinning corpse in a vacuum is silent. Astronomers theorize these ultra-long period objects must be enveloped by a dense cloud of material, a circumstellar nebula or a disk of leftover gas from their formation. As the object spins, its powerful magnetic field acts like a dynamo, stirring up this cloud, accelerating particles within it, and ultimately lighting it up like a neon sign. The slow period we observe, then, might not just be the spin of the star itself. It could be the rhythm of how this magnetic dynamo interacts with its surrounding shroud of gas. The cloud acts as both a fuel source and a moderator, controlling the release of energy and stretching what might be a faster process into the long, luminous pulses we detect. These LOFAR discoveries are more than just new objects. They are glimpses into a previously invisible layer of cosmic behavior, where time itself seems to stretch, and where the secret to the signal lies not just in the star, but in the thick, magnetized fog that clings to it. The slow, majestic pulses from LOFAR discoveries exist at one extreme of cosmic time, but our own galactic neighborhood holds objects that pulse with a more frantic, furious energy. Brown dwarfs occupy a strange twilight zone in the cosmos, objects too massive to be called planets, yet not massive enough to ignite sustained hydrogen fusion in their cores. For decades, they were considered dark, silent failures, fading embers drifting between the stars. Then radio telescopes began to listen, and the silence broke in a spectacular way. These so-called failed stars were screaming. Astronomers detected intense, pulsed radio flares erupting from brown dwarfs, bursts of coherent radiation so powerful they outshone anything our own sun produces in radio wavelength. This was a complete shock. Standard models of brown dwarf magnetospheres, the regions dominated by their magnetic fields, could not explain such brilliant, organized outbursts. The key to the mystery lies not in stellar fusion, but in a process we know well from our own solar system, auroras. On Earth, the northern lights are created when charged particles from the solar wind spiral down our planet's magnetic field lines, striking the atmosphere. Jupiter has auroras thousands of times more powerful, fueled by particles spewed from its volcanic moon Io. Brown dwarfs take this concept to a staggering extreme. Imagine a magnetic field hundreds of times stronger than Jupiter's, coupled with a turbulent atmosphere swirling with powerful storms. Charged particles, perhaps stripped from a close orbiting planet or accelerated within the brown dwarf's own atmosphere, get caught in this ferocious magnetic grip. They rain down onto the object's upper atmosphere, but with such energy that they generate not just shimmering light, but a lighthouse beam of coherent radio waves. This coherence is what makes the signal so strong and detectable across interstellar space. Unlike the random static of thermal emission, coherent radio waves are all in step, like a laser beam of sound, amplifying their power dramatically. This discovery did more than just surprise us, it handed astronomers a revolutionary new tool. By studying the rhythm and strength of these radio pulses, we can now map the invisible magnetic fields of brown dwarfs, measure their rotation speeds, and even probe the chaotic weather in their alien atmospheres. A faint, flickering object once written off as a dark cinder has been transformed into a brilliant beacon, its pulsed radio screams revealing the violent and beautiful physics of magnetic storms on a scale we are only beginning to understand. Brown dwarfs reveal the hidden ferocity of failed stars, but to witness the raw, explosive power of the cosmos, we must look far beyond our galactic backyard. In a stunning recent discovery, the Deep Synoptic Array in California pinpointed the most distant fast radio burst ever recorded. This signal, designated FRB 2000-20610A, did not come from a nearby galaxy. Its source lies in a small group of galaxies so incredibly far away that its light has been traveling for over 8 billion years to reach us. To put that in perspective, this burst erupted when our universe was less than half its current age, and our own solar system did not yet exist. The energy released in that fleeting millisecond is almost beyond comprehension, equivalent to our sun's total output over 30 years unleashed in an instant. But the true value of this cosmic cannon blast is not just its power, it is the unprecedented journey its signal took. As this burst raced across the universe for billions of years, it passed through an unimaginable volume of space, traversing the diffuse plasma that fills the vast voids between galaxy clusters and filaments. This material, known as the cosmic web, is the large-scale structure of the universe, a network of thin, ionized gas that is notoriously difficult to detect directly. The fast radio burst from this high redshift galaxy acted like the ultimate scientific probe. Its radio waves were subtly slowed by every electron they encountered along the way, a delay we measure as dispersion. The dispersion for this burst was colossal, the highest ever recorded. By carefully subtracting the known contributions from our own Milky Way and the host galaxy, astronomers were left with a precise measurement of the total amount of ionized material the signal passed through in intergalactic space. This measurement is a landmark. It provides one of the cleanest confirmations yet for the predicted density of the cosmic web. The diffuse gas that theory says should contain a large portion of the universe's normal matter that has been frustratingly missing from our previous inventories. This single ancient flash is helping to solve the cosmic missing matter problem, proving that the material is out there, spread thinly across the immense voids just as models predicted. It transforms a mysterious cataclysm into a precision tool, using the echo of a distant explosion to illuminate the invisible scaffolding of the entire cosmos. The most distant burst illuminates the cosmic web, but one of the most brilliant flashes of all comes from a source we know intimately. In the heart of the Crab Nebula, the expanding wreckage of a supernova witnessed in the year 1054 spins a city-sized cinder. The Crab pulsar rotates 30 times every second, flashing like a cosmic lighthouse with a regularity so precise it rivals atomic clocks. Yet, buried within this metronomic tick is a shocking anomaly, the giant pulse. On rare, unpredictable occasions, this pulsar does not just flash, it screams. A single rotation can unleash a radio burst millions of times brighter than its normal pulse, a spike of raw energy so intense it can be detected across the galaxy. These are not mere variations, they are monstrous outbursts that defy the steady behavior we associate with these celestial timekeepers. The giant pulses are so powerful they momentarily outshine the entire surrounding Crab Nebula in radio waves, a testament to their staggering concentration of energy. What could cause such a violent departure from the norm? The secret likely lies in the chaotic environment the pulsar calls home. The Crab pulsar is not spinning in empty space, it is embedded deep within the turbulent cloud of gas and dust that is the nebula itself, the very remains of the star that died to create it. Theorists believe these giant pulses may be triggered by plasma instabilities, sudden and catastrophic rearrangements within the pulsar's own fiercely magnetized atmosphere, its magnetosphere. Picture the magnetic field around the neutron star as a complex, writhing web of energy. Under certain conditions, this web can snap, releasing a vast store of pent-up power in a single, coherent blast of radio waves. But the surrounding nebula may play a crucial role as a catalyst or an amplifier. Dense knots of gas from the supernova remnant could drift into the pulsar's path, interacting violently with its magnetic field and sparking an avalanche of particle acceleration. Alternatively, the nebula's own magnetic fields might temporarily align with the pulsars in just the right way to focus and magnify its emission, turning a steady beam into a blinding searchlight. These giant pulses push the very physics of coherent emission to its absolute limit, demonstrating how a known object in a specific and dynamic environment can still produce bursts of power that dwarf our understanding. They are a reminder that even the most familiar cosmic landmarks can harbor profound and explosive secrets. From the brilliant radio screams of pulsars, we shift our gaze to a different kind of light, a warmer, more subtle glow that paints the spaces between the stars. When astronomers point infrared telescopes at vast clouds of interstellar gas, they see more than just a featureless haze. The spectra, the chemical fingerprints of this light, are crisscrossed by a series of mysterious broad emission bands. These are the unidentified infrared bands, and they are among the most widespread and puzzling signatures in our galaxy. They appear in nebulas in the diffuse gas of the Milky Way, and even in other galaxies, telling us that whatever is producing them is a fundamental component of the cosmic landscape. For decades, their origin was a complete enigma. Then, a compelling suspect emerged from laboratory chemistry here on Earth, a class of large, sturdy molecules known as polycyclic aromatic hydrocarbons, or PAH. Picture the molecular structure of soot or the arrangement of atoms in a charcoal briquette, complex rings of carbon and hydrogen linked together in flat, plate-like formations. These molecules are remarkably robust, and when they are jostled or energized by starlight, they vibrate in specific ways, emitting infrared light at very distinct wavelengths. The pattern of the unidentified infrared bands matches what we would expect from a family of these pH molecules astonishingly well. It seemed the case was closed, a beautiful marriage of astrophysical observation and terrestrial chemistry. But the universe is rarely so tidy. The exact identity of the molecules responsible for each specific band remains elusive. We are likely seeing a mixed population, a cosmic cocktail of different pHs and perhaps other large carbon-bearing molecules, all contributing to the blended signal. Even more perplexing is the environment in which we find them. These bands shine brightly in places bathed in the intense, harsh ultraviolet radiation from young, massive stars, regions where you would expect such complex organic molecules to be torn apart. Their survival is a profound puzzle. How do these large molecules form and persist in such violent conditions? Do they form right there in the turbulent gas clouds, or are they forged in the atmospheres of dying stars and then ejected into space like cosmic seeds? The presence of these infrared bands is more than a chemical curiosity. It is a direct clue to the cosmic cycle of carbon, one of the essential building blocks of life. They represent a missing link between simple atoms and the complex organic chemistry that could eventually lead to planets and perhaps biology. So while we call them unidentified, they are really an invitation, a faint infrared whisper from the gas clouds themselves, hinting at a rich and complex chemical universe happening right in the dark, cold spaces between the stars. The infrared whispers of complex molecules are not the only strange light emanating from the void. Deep within the radio and microwave sky, there exists a faint, enigmatic glow that defied categorization for years. It is called anomalous microwave emission, and it was a ghost hiding in plain sight. For decades, astronomers mapping the cosmic microwave background, the ancient afterglow of the Big Bang itself, kept finding patches of extra microwave light that did not fit the smooth, uniform profile they expected. At first, these were considered potential anomalies in the primordial signal, hints of something fundamental about the early universe, but as observations improved, a pattern emerged. This extra glow was not coming uniformly from deep space. It was tightly correlated with something much closer to home, dense clouds of interstellar dust within our own Milky Way. This was not a relic of creation, it was a local mystery. The emission was brightest in specific frequency bands between 10 and 60 gigahertz, a range that sits between traditional radio waves and far infrared light. None of the known processes could explain it. It was not thermal radiation from warm dust, nor was it synchrotron radiation from electrons spiraling in magnetic fields. The signal was something entirely new. The breakthrough came from a surprising suspect, the smallest pieces of dust in the cosmos. Imagine a grain of interstellar dust, but not the kind you might picture. These are nanoparticles, mere billionths of a meter across, smaller than a virus. Theorists propose that these tiny grains, likely made of carbon or silicates and perhaps coated in a mantle of icy molecules, could be spinning at phenomenal rates, billions of times per second. What could cause such frantic motion? They are buffeted by collisions with individual atoms, struck by photons of starlight, and even torqued by their own internal magnetic properties. This incredible spin gives them an electrical charge that fluctuates rapidly, and according to the laws of electromagnetism, a spinning dipole emits radiation. For these nanograins, that radiation falls precisely in the anomalous microwave range. It is a form of rotational light, a faint hum generated by the dizzying dance of cosmic motes. This discovery added a whole new component to our inventory of interstellar material. We now understand that the space between stars is not just filled with gas and large dust grains, but also with this fine, spinning dust that paints the galaxy with a subtle microwave sheen. These nanoparticles are likely the shattered fragments of larger grains, destroyed in shockwaves from supernova or in the violent winds of massive stars. Their presence and their strange emission tell a story of constant cosmic recycling, where dust is born, shattered, and spun into a luminous fog that fills the galactic clouds, a hidden layer of the interstellar medium finally revealed by its own quiet, persistent whisper. While the spinning dust hums in microwaves, a far older mystery lies hidden in plain sight, written in shadows across the light of distant stars. For over a century, astronomers have known that the light from stars, when broken into its rainbow spectrum, is not perfectly smooth. Interspersed among the familiar dark lines caused by atoms in the star's own atmosphere are hundreds of other, much broader and shallower absorption lines. These are the diffuse interstellar bands, and they are not born in the stars. They are imprinted on the starlight as it journeys to us, absorbed by something lurking in the vast clouds of gas and dust between the stars. Think of it like this: you are looking at a bright lighthouse through a thick, mysterious fog. The fog itself leaves a specific, complex pattern of shadows on the beam, a fingerprint of everything floating within it. That is what the diffuse interstellar bands are, the collective fingerprint of unknown molecules drifting in the cosmic fog of our galaxy. The sheer number of these bands is staggering, with over 400 identified, and each one represents a specific quantum leap of a molecule, a unique note in a complex chemical symphony we cannot yet read. For decades, the identity of the molecules responsible, called the carriers, has been one of the most enduring puzzles in astrochemistry. We know they are not simple atoms or small molecules like hydrogen or carbon monoxide. Those leave sharp, narrow lines. These bands are broad and diffuse, telling us the carriers are large, complex, and stable enough to survive the harsh radiation of interstellar space. The hunt has focused on two leading families of suspects. The first are carbon chains, long strings of carbon atoms, sometimes with other atoms like nitrogen or magnesium at their ends. These are the skeletal frameworks of larger organic molecules. and some laboratory experiments have shown they can produce absorption features eerily similar to a few of the diffuse bands. The other, more exotic candidates are fullerenes, soccer ball-shaped cages of carbon atoms. The most famous of these, Buckminster fullerene, or C60, is a molecule of 60 carbon atoms arranged in a perfect sphere. Its discovery on Earth won a Nobel Prize, and there is strong evidence it exists in space, but pinning it definitively to a specific diffuse band has been a challenge. Why does solving this century-old mystery matter so profoundly? Because these unidentified molecules are likely the intermediate steps, the missing links, in the cosmic chemical pathway that leads from simple atoms to the complex organic chemistry necessary for life. They are the prebiotic inventory of the galaxy, floating in the nurseries where stars and planets form. When a new solar system coalesces from a cloud rich with these molecules, that complex chemistry is baked into the recipe from the very beginning, potentially seeding young worlds with the building blocks for biology. Identifying even one carrier would be a Rosetta Stone moment, unlocking not just a chemical identity, but a window into the processes that build complexity in the cold, dark voids. These dark lines in starlight are more than just a spectroscopic puzzle. They are a chemical census of the interstellar medium, a hidden library written in shadows, waiting for us to learn its language. The diffuse interstellar bands are a chemical mystery written in starlight, but to witness the raw physics of matter under siege, we must look to a far more violent partnership. In the crowded stellar neighborhoods of our galaxy, a deadly dance plays out in X-rays. These are X-ray binaries, systems where a neutron star or a black hole, the remnant of a supernova, orbits a normal star so closely that it strips material from its companion. This stolen gas does not fall directly onto the monster. Instead, it spirals inward, forming a vast, whirling disk of superheated plasma called an accretion disk, a cosmic hurricane of gas screaming toward oblivion. As this material nears the event horizon of the black hole or the solid surface of a neutron star, it is compressed and heated to millions of degrees, blazing with high-energy X-rays. But the light from these systems is not a steady beacon. It flickers, flares, and pulses in wild, chaotic patterns. Embedded within this frenzy are brief, rhythmic signals known as quasi-periodic oscillations, mysterious X-ray hums that rise and fall in frequency like a siren winding up and down. These oscillations are the heartbeat of chaos itself, generated by the very turbulence in the accretion disk. Think of the final moments before a waterfall. The water does not flow smoothly, it churns and forms violent whirlpools. In an accretion disk, blobs of superheated gas orbit at the very edge of the point of no return, and their frantic motion creates shock waves and vibrations that ripple through the entire disk. These vibrations modulate the X-ray output, creating the quasi-periodic signal. For astronomers, these flickers are a priceless tool. By studying their frequency and how they change, we can map the extreme space-time around a black hole, testing Einstein's theory of gravity in environments where it is stretched to the limit. The oscillations can reveal the spin of the black hole and the properties of the innermost stable orbit, the final circular path matter can take before its fatal plunge. Yet, for all their utility, these signals still hold profound puzzles. Why do the oscillations sometimes vanish entirely? What triggers the sudden, colossal X-ray flares that can briefly outshine an entire galaxy? The answers may lie in the magnetic personality of the gas itself. The accretion disk is not just hot plasma, it is a magnetized fluid. Intense magnetic fields, twisted and amplified by the disk's insane rotation, can snap like rubber bands, releasing enormous bursts of energy that catapult matter away in jets or cause the entire inner disk to suddenly brighten in a violent flare. The quasi-periodic oscillations, then, are not just a simple vibration. They are the complex resonance of a magnetized storm, a whirlpool of gas fighting against the grip of gravity and its own internal magnetic forces. Each flicker in the X-ray light is a coded message from the edge of a gravitational abyss, a direct probe into the physics of matter, magnetism, and gravity operating under the most extreme conditions imaginable. The furious X-ray flickers from a crescent disk show us matter in its final, desperate moments, but there are explosions in the cosmos that make even those cataclysms seem tame. Gamma-ray bursts are the most violent events since the Big Bang itself, titanic detonations that for a few seconds can outshine every star in the universe combined. We believe we understand the engine behind them, the catastrophic collapse of a massive star into a black hole or the merger of two neutron stars, events that launch ultra-relativistic jets of material piercing through space at nearly the speed of light. It is the aftermath of these blasts, however, that holds a deeper, more persistent mystery. After the initial gamma-ray flash fades, it leaves behind a fading ember called the afterglow, visible for days or weeks in X-ray, optical, and radio wavelengths. This afterglow is the expanding shockwave from the jet, plowing into the surrounding interstellar medium and lighting it up. In a smooth, uniform universe, this afterglow should fade in a predictable, steady decline. But the universe is not smooth. Time and again, astronomers watching these afterglows see something strange. The fading light will suddenly halt its decline, plateau for a day, or even violently re-brighten, creating a distinct bump in the light curve. It is as if a dying fire were suddenly doused with gasoline. These bumps are not random noise, they are vital clues. They tell us the jet from the gamma-ray burst is not traveling through empty space. It is slamming into dense, lumpy clouds of gas that were floating in its path long before the star ever died. Imagine a tsunami wave rushing across the ocean. If it hits a solitary island, the water piles up and surges over it, creating a secondary, chaotic peak of energy. The gamma-ray burst jet acts in the same way. When its leading shockwave collides with a particularly dense knot of interstellar material, the interaction re-energizes the entire system. Fresh particles are accelerated to extreme speeds, causing the fading afterglow to flare back to life in a brilliant radio or optical rebrightening. Each bump in the light curve is therefore a forensic marker, a signpost of a single gas cloud in a galaxy billions of light-years away. By modeling these bumps, astronomers can perform remote sensing on an impossible scale. They can estimate the density of those distant clouds, their distance from the burst, and even map the clumpy, uneven distribution of gas in the host galaxy's interstellar medium. This transforms the afterglow from a simple fading echo into a dynamic probe. We are not just watching an explosion fade, we are watching that explosion illuminate in real time the hidden architecture of a far-off galaxy. The unpredictable bumps are a detailed diary of the journey, a record of every substantial cloud the jet encountered on its way out of its galactic home. They reveal that the sites of these universe-shattering explosions are not clean rooms, but messy, complex neighborhoods where titanic forces must fight their way through a fog of ancient gas before their light can finally reach us across the cosmic deep. The unpredictable bumps in gamma-ray burst afterglows reveal a cosmos of hidden clouds, but one fast radio burst source presents an environment so extreme it defies every category. Signal 25 is not just a repeater, it is a double mystery. FRB 2019-0520b is one of the most active repeating bursts we know, but it shares its location with something utterly unique, a persistent, compact radio source. This is not a fleeting flash beside a quiet star. It is a brilliant, constant radio beacon sitting right next to the object that sporadically erupts in even more brilliant flashes. This pairing is unprecedented, and it forces us to envision a scene of staggering violence and energy. What could possibly produce both a steady radio hum and intermittent, universe-spanning screams? Astronomers are wrestling with three radical possibilities, each painting a different portrait of this chaotic corner of space. The first theory imagines a newborn magnetar, still swaddled in the wreckage of its birth. When a massive star goes supernova, it can leave behind a highly magnetized neutron star, and that newborn object would be embedded in an expanding cloud of its own stellar remains. If the magnetar is young and spinning furiously, its powerful wind of particles could continuously slam into that surrounding cloud, lighting it up as a permanent, bright radio nebula. The fast radio bursts would then be occasional, more violent eruptions from the magnetar itself, perhaps massive starquakes on its crust, superimposed over the constant glow of its agitated cradle. The second possibility looks to a more ancient cataclysm. Perhaps the persistent source is not a nebula powered by today's activity, but the shocked aftermath of a past explosion. Imagine the remnant of a previous colossal flare from the magnetar, a shell of material blasted out long ago that is still expanding and glowing as it plows into the interstellar medium. The repeater we see now would be the same object, having settled into a new phase of occasional outbursts, while the ghost of its former fury still shines beside it. The third and most exotic idea challenges our very assumption about the source's scale. Could the persistent radio source be something entirely separate and monumental, like an active galactic nucleus, a supermassive black hole feeding at the heart of its galaxy? In this scenario, the fast radio bursts might be produced by a magnetar or some other object orbiting perilously close to that central monster. The constant radio glow would be the roar of the black hole's accretion disk, a galactic scale background against which the tiny, brilliant flashes of the burst appear. This would place the FRB in the most energetic environment possible, a cosmic maelstrom where the laws of physics are stretched to their breaking point. The co-location of these two phenomena is a direct challenge. It tells us that whatever engine creates FRB 2019-0520b, it exists within an environment that is continuously pouring out enormous radio energy. This is not a quiet neighborhood. It is a place of perpetual storm where the interstellar medium is not a passive fog, but a luminous, excited plasma, forever stirred and heated by a hidden, ferocious power. Solving this double mystery may require us to stop thinking of fast radio bursts as isolated explosions and start seeing them as symptoms of a much larger, more sustained cosmic upheaval, where the boundary between the source and its environment completely dissolves. This double mystery of a persistent radio source beside a brilliant repeater forces a profound and unsettling question. If the universe is so filled with such violent, complex, and energetic phenomena, then where is the evidence of anyone else building amidst this chaos? This brings us to the haunting heart of the matter, the Fermi Paradox and its shadow, the Great Filter. Physicist Enrico Fermi famously posed the question during a casual lunch conversation in the middle of the 20th century. Given the vast age of the universe and the sheer number of stars with planets, it seems statistically inevitable that other technological civilizations should have arisen. They should have had ample time to spread across the galaxy, their presence obvious, yet we see no clear signs. Where is everybody? The growing catalogue of unexplained signals we have explored does not answer this paradox, it deepens it in a chilling way. We are discovering that the cosmos is not a quiet, empty stage waiting for actors. It is a roaring, dangerous amphitheater of natural violence. Gamma-ray bursts sterilize regions of space, magnetar flares unleash apocalyptic magnetism, and cosmic rays bombard worlds with lethal radiation. The interstellar medium itself is a complex chemical soup and a turbulent magnetic maze. This cosmic environment presents the first possible layer of a great filter, a hypothesized barrier that prevents life from advancing to the stage of interstellar communication or travel. Perhaps the filter is simply the rarity of a planet maintaining stable, benign conditions long enough for intelligent technology building life to evolve amidst a galaxy that is constantly shooting cosmic bullets. But the signals introduce another, more subtle possibility. What if the filter is not silence but confusion? Our entire search for extraterrestrial intelligence is predicated on the idea that a technological civilization will produce a clear, artificial signal we can recognize, like a deliberate radio beacon. Yet, what we are actually finding are countless natural signals of breathtaking complexity, signals that often mimic the very signatures we theorize an artificial one might have. The wow signal's perfect frequency, the clockwork periodicity of some repeaters, the narrowband whispers from sun-like stars, these all briefly raised our hopes before being absorbed back into the natural, if poorly understood, world. This creates a terrifying bottleneck of interpretation. If a real, deliberate message from another civilization arrived tomorrow, how would we know? Would it be lost in the cacophony of magnetar pulses and scattering from interstellar plasma? Would we dismiss it as just another fascinating natural anomaly, another entry in a catalogue of cosmic mysteries? The great filter then might be epistemological. It might be the sheer difficulty of distinguishing a technological needle in a cosmic haystack that is itself made of glittering, mysterious metallic threads. Our inability to explain so many of these signals with certainty could be a preview of our permanent state, forever listening to a universe shouting in a language of natural cataclysm, while a faint, deliberate whisper hides in plain sight, indistinguishable from the storm. The profound silence we confront might simply be a failure of perception. Our current telescopes are like straining to hear a whisper in a hurricane, but that is about to change. A new era of cosmic eavesdropping is dawning, powered by instruments of such staggering scale and sensitivity they will redefine the search entirely. Leading this revolution is the Square Kilometre Array, the SKA. When completed later this decade, it will not be a single dish, but a vast network of thousands of antennas spread across South Africa and Australia, forming a collective radio ear with a total collecting area of, as the name suggests, 1 square kilometre. Its capabilities are almost mythical. The SKA will be so sensitive it could detect an airport radar on a planet orbiting a star tens of light years away. For the mystery of fast radio bursts and other transient signals, this is a game changer. The SKA is predicted to detect not dozens, not hundreds, but potentially thousands of these bursts every single day. It will not just catch them, it will dissect them with surgical precision, measuring their polarization, their fine scale structure, and their dispersion with unprecedented detail. This torrent of data will allow us to finally categorize these events, separating the true one-off cataclysms from the erratic repeaters, and perhaps revealing entirely new, unforeseen classes of radio transients. It could pinpoint the source of a burst to a specific star cluster, a supernova remnant, or even an individual object within a distant galaxy, turning statistical mysteries into tangible cosmic laboratories. While the SKA listens to the radio sky, another monumental project will watch it with an all-seeing optical eye. The Vera C. Rubin Observatory, perched atop a mountain in Chile, houses the largest digital camera ever built. Over a decade, it will conduct the legacy survey of space and time, scanning the entire southern sky every few nights. It will not hunt for radio waves, but for the fleeting optical counterparts of cosmic explosions. When a fast radio burst or a gamma-ray burst goes off, the Rubin Observatory might catch the faint, fading afterglow in visible light, providing a crucial second color to the portrait. More importantly, its relentless survey will catch unpredictable stellar flares, mysterious optical transients, and the violent deaths of stars, events that might be linked to the radio signals we detect. By correlating the optical fireworks with the radio screams, we can begin to build a complete picture of the catastrophe, understanding the full spectrum of energy released when a magnetar quakes or neutron stars collide. This coming flood of data presents its own colossal challenge. The SKA and Rubin Observatory will generate more information in a single night than all of astronomy did in its first century. No team of human scientists could possibly sift through it all. This is where our own technology becomes the essential partner. Advanced machine learning algorithms trained on the signals we already know will be set loose on this digital ocean. They will act as tireless sentinels, flagging the unusual, the repetitive, and the statistically impossible in real time, separating the potential discoveries from the background noise of the universe and our own instruments. But the human element will remain vital. Citizen science projects where volunteers around the world examine snippets of data will continue to play a crucial role. The human brain is still unmatched at pattern recognition, at noticing the odd detail a pre-programmed algorithm might dismiss. This partnership between silicon and human curiosity will be our net cast wide into the deepest cosmic seas. The goal of this next generation is not just more data, but clarity. With thousands of localized bursts, we will see if patterns emerge, linking them to specific galactic environments, stellar ages, or chemical abundances. We may finally identify the exact molecule responsible for a key diffuse interstellar band, or catch a brown dwarf's auroral pulse in the act of flaring. We could witness the birth of a magnetar in real time, watching its first furious outbursts and the glowing nebula that forms around it. The old mysteries, from the WOW signal to the galactic center radio transient, will be reobserved with these powerful new tools, perhaps revealing faint, repeating whispers we missed the first time. The coming decade promises to transform our catalog of cosmic anomalies from a list of puzzling exceptions into a rich taxonomy of natural phenomena. And in doing so, it will sharpen our search to an exquisite point, filtering out the roar of the natural universe so that if a true, deliberate signal is out there, its artificial whisper will finally ring clear and unmistakable against the newly mapped cacophony of the stars. These 25 cosmic whispers form a map of our own wonder. From the solitary, perfect frequency of the WOW signal to the rhythmic heartbeats of repeating bursts and the ancient chemical signatures in starlight, each is a beacon in the dark. But they do not illuminate answers, they illuminate the vast and beautiful terrain of our own ignorance. Every unexplained chirp, every flicker from a galactic core, and every mysterious absorption band is a question shouted across space and time, a challenge to our understanding of physics, chemistry, and our place in the cosmos. Some are almost certainly the natural death cries of stars or the birth pangs of exotic objects. Others linger in that tantalizing space where nature's creativity brushes against the possibility of something more. Yet their true value is not in a final, simple label. Their power is in the pursuit they inspire. Each one is a compass needle pointing not to a destination, but to the next horizon of discovery, driving us to build more sensitive telescopes, devise more clever algorithms, and ask more profound questions. So the next time you look up at a clear night sky, remember this: you are not looking at a static picture. You are gazing into a dynamic, chaotic, and deeply mysterious conversation. It is a conversation carried on the solar wind, etched into the light of distant stars, and whispered by clouds of gas between the galaxies. We have only just begun to listen. Stay curious, the universe is still speaking, and its greatest secrets have yet to be decoded.